So in the last little video, we looked at some basic mixing models and essentially how to get ecologically relevant information from stable isotope data. And in this video, we're going to take things on a step a little bit further. The last time we looked at a very straightforward two-source, two-end-member mixing model, estimating things in terms of benthic or pelagic resource use in terms of the question. But quite often we're interested in things that are a little bit more complicated. And for example, in the lake systems that we're looking at here, we're not just really interested in whether things are separated on a pelagic littoral axis. We also have that profundo zone, that deep water zone. And that's possibly a source that some of the fish are feeding in. So we want to be able to incorporate that. And we also want to be able to incorporate things like estimates of error on our end members. So we've got an estimate of what that source value is. Remember the two-source mixing model, we could just give a single value for that, but we know that's not correct. So we want to use a more robust system that will allow us to put variation on that or account for variability in that. We also want to be able to account for variability in the trophic fractionation values. We know that they can be, they're not as simple as just one number. So we need a way to handle that. And this is where the advent of these things like the mixer and SIMMR a good few years ago, and more recently what we're going to look at now, things like SIMMR and mixer, sort of the next generation of those models, using a Bayesian approach to estimate based off population estimates or distribution estimates rather, to estimate the contribution of a source to a population, to a consumer population. So to do this, what we're going to, we need things to be a little bit, it's a little bit more difficult, than or a little bit more complicated, let's say, at least the mathematics is, than what we dealt with in the previous lecture. So, but how we're going to go through it is almost the exact same way. We're just going to run with our same worked example, and I'm going to run you through some scripts and show you how it works, and we'll sort of look at some of the outputs from that, figure out what it all means. So what you should have is, in fact, what I'm going to have to do, I'm going to start sharing my screen here. And what I'm going to do, I'm going to share this entire screen. And then you all should be able to see what I need you to see. Okay, so first of all, start with something like this. So I've shared these different input files, same as the last course, so last videos. We've got a folder that has all the files. We've got our prelim file, but we also have some of these specific input files, and I'll explain that in a minute. But essentially what this is because the mathematics is more complicated, the package will do all that work for us. But the package needs to have the package, essentially the software. It needs to have the input files in a particular type of format that it's able to use. So we have to make sure our input files and our data is put into that format, and then we give that to the package, and it can do the analysis for us. So let's say, for example, we want to have SIMMR cons, which is our consumer data. Okay, so we're just going to open this up and have a quick look at it. So we've got code here for species. So we've got 1 species and 2. Okay, so here our species are coded as 1 and 2 as opposed to actual names. That has to be a number. And then we've got the isotope ratios for those consumers. So again, we need to strip out all that other information that we had in the files that we were using yesterday and just pare it down to the actual raw input files that go into the program. Okay, that's what they look like. We're going to get to that in a moment. Before I go much further, I'm going to say that the analysis we're doing here was developed by the package SIMMR. We're going to start with SIMMR. It's a bit simpler, and then we move on to mixer in the next lecture, or the next little video. Was developed by these two guys, by Andrew Parnell and Rich Inger, who've developed the SIMMR package. it builds off work that Parnell and Richinger and a couple of others did with Andrew Jackson developing the SIMMR, Stable Isotope Analysis in OR. And this is kind of a variant of that. And this is a website I've linked to. There's a link to this in the script. And you'll see they keep it pretty up to date with, it's almost like a README, but a lot of worked examples, an absolute treasure trove of information about these packages. And you need to do with these packages. These guys have shown you how to do it. Yeah. So I'm going to work through a quick worked example here. A lot of what I'm using is sort of applying what they have here in their worked examples, but with the data that we talked about yesterday. But use this to when you're applying this to your own data for your own studies and your own models. Okay, so let's bring in our OR Studio, and it should be looking familiar to all of you by now, hopefully. I'm just going to fit this to the size of my screen. Okay, so we're not going to talk about what this is in terms of the or markdowns and all that type of stuff now, but essentially, you remember from previous videos, what we've got here is boxes of code with the actual, or the boxes of script where we actually run the code, and then annotated notes around it. Yeah, and again, we've got a link in here to the stuff, to the website that I just referred to. Okay, so what are we going to do? What we're going to do is similar analysis to what we did yesterday, but here we're going to look at it in terms of three potential sources. Instead of just littoral and pelagic, we now have littoral, pelagic, and also profundal, that deep water. Yeah, okay, so let's load the packages we need. Let's load in our data. You'll see we're not now rolling on from, this is an entirely new script, a new OR project just tailored for this, completely different to what we worked with yesterday. Yeah, so again, we need to input our data and get everything up and running. First, we want to pick out what our source values are going to be here. And similar to what we did in the previous lecture, we want to make it sort of a summary table, and we can have a look at that. And we're going to blow this up here and we can have a look. Now, so we've got two lakes, say exact same as yesterday, Lake Kivi, Lake Volantis. We've got classes or classifications, littoral, profundal, zooplankton, the mean and standard deviation of carbon, the same for nitrogen, the percent C, mean and standard deviation, percent N, mean and standard deviation, and the sample size, the actual number of individuals that went in to make these distributions. I'm not going to go through in great detail the theory behind what we're doing here. We've covered that in the lectures, and or depending the time you're viewing this, we will cover that in the lectures. And I don't want to overburden you with information right now. So right now we're just going to sort of work through the mechanics, the nuts and bolts of how this works. So what we need to do is scroll down to the next part. And so that's our data. And that's essentially what we've made our input files from. And these are the input files we had a look at earlier. And if I run this, essentially what we're doing is picking up each of those input files, importing it into OR and giving it a name. So we've got mixed data is our SIMMR_cons.csv, so that's our consumers. We've got sources, we've got corrections, which is the trophic enrichment factors, and we've got concentrations. So all of that goes in as separate files and is then in as different data frames, as different OR objects that the package can take and work with. Okay, so the next thing we need to do is to put all this together and essentially build the model. So what we're doing here, you'll see we're picking up each of those different input files, pulling out bits and pieces of the information, and creating an object that the package needs to run the model. So click go on that and let that run through. And then we can sort of do start doing some quick plots to have a look and see what we've got. Yeah. And here's our first plot. And the first thing to note here, so we're calling this an isospace plot for Lake Vuontas. We're just looking at Lake Vuontas here. This is one of the limitations of the SIMMR approach, that it can only handle one model at a time. Yeah. So where we're doing two different lakes, and we want to look at the difference between those two lakes, we need to run those lakes independently and then compare the results sort of post hoc afterwards. But if we remember, we've got Lake Vuontas. This was the deeper lake that we looked at yesterday. We've got our three different sources now. We've got littoral invertebrates over here. We've got our zooplankton up there, and we also have profundal or deep water invertebrates. And then we've got what's titled as mixtures 1 and mixtures 2, which are our two consumer species, our two fishes. Here's fish species 1, fish species 2. Species 1 is closer to the littoral. No, excuse me, species 2 is closer to the littoral. Species 1 is more intermediate between the two. So this essentially, if you remember back to the previous lecture, or the previous video, perch, predominantly associated with littoral, whitefish, more so intermediate. Okay, so all we're doing here is we're seeing the same thing. And the other thing to note is that the source values here have been corrected by the trophic enrichment factors. And what we would expect, what we want really, is for all the consumer data to fall within a polygon of denoted by sort of the extreme outpoints on those sources. And you can see we've got a couple of outliers, but for the most part, we're not too bad. We're not too far away. If you've got a situation where you've got a load of data points up here that are way outside the polygon, then that's something you're going to need to look at, because likely you're missing a source or something like that. We'll talk about that in more detail in the class. Okay, so we've inputted our data. We've had a quick plot just to make sure everything looks okay, and we haven't put in the wrong files, or the trophic enrichment factors aren't wrong. If you put in the data with the trophic, say you put in an extra 0 or misplaced a decimal place or something like that somewhere in your file, straight away you'll see it here, and it saves you a bit of time further down the road than running models and trying to deal with the error messages and whatnot. Okay, so next thing, we've got everything in. Next thing we need to do is to press go and to actually run the model. And it's we don't have too many consumers. We've only got one lake system, so it's pretty quick. It doesn't take too long. One of the nice things about SIMMR, and certainly when we compare it with Mixire and things later on, that it's a much, much quicker model. It said while waiting for it. So essentially what it's doing, it's running the mixture for group 1, and then it'll run the model for group 2, and there we have a couple of seconds, bing bang bang, we're all done. Okay, so the model is now run, that's finished. First thing we want to do, we want to test whether the model has actually converged. Well, again, we'll talk about that a bit more in class, but essentially whether the model results are reliable, and we're happy to move forward with this and trust the results that it's giving us. So the first thing to do here is, so essentially in SIMMR, this is based around these Gell-Mann diagnostics, and we want to get values that are close to 1. So there's one of the things I like about the SIMMR package is it's really user-friendly, really intuitive. There's not too many different things that you have to figure out. A lot of what we're going to do is essentially we've created this SIMMR out. That's the results of our model, the output of our model, let's say. And then we can use this call summary and say what different type of things we want. And the vast majority of things we need to know about this, we can get by just changing the aspects in this summary call. And I'm going to go through some here. There's a lot more listed on that website that I shared earlier. So let's say we want to look at our diagnostics, summary for group 1, summary for group 2. Our Gell-Mann diagnostics, values should all be close to 1. And as we run across, everything is exactly 1 for both groups. So we're really happy with this. The model has converged. Like we noticed, there was a couple little outliers, but it's not enough to cause a big problem for the model. So we can be confident in our data going forward. Another thing we might want to do is just to have a look at this, and essentially what we're looking at here is the predicted versus observed outputs based on the model, similar to what you might be looking at if you look at the various residual plots on GLNs and things like that. There you go, guys, again. Okay. And again, here, what we want is these observed values here to fall pretty much somewhere within the within that range, and barring one or two outliers, we're pretty much there. So we're confident in this going forward, that when we look at the actual results from this, of the output from this model, that the model has worked. So we've checked the data going in the plot. We know everything there looks about right. We've checked that the model worked. Everything there looks about right. Now we can take the next step on and look at the actual outputs. So we may want to do that. Yeah. Shut down Outlook. So there'll be no more. We won't be interrupted by emails anymore. Okay, so let's press go on this, and we get our summary for group 1 and our group 2. So we get a couple of different ways of looking at this. We can look at the mean and standard deviation across the group, and this is the contribution of each source to this specific group. And these should just about sum to 1. So for group 1, we've got littoral, makes up around about 23%, 24%, profundal are around about 17%, and zooplankton around about 60%. And we've got standard error on each of those. So a large contribution of pelagic, but a moderate contribution of littoral and profundal as well. Move to group 2. What do we see? Littoral, almost 70%. Profundal, 10%. Zooplankton, 20%, something like that. So again, we've got a much bigger littoral contribution here. We can put an error estimate around that, and so on. The other thing we might want to do is, instead of looking at that as means and standard deviations, we can actually export the quantiles for this. And here we're looking at sort of the mode value, so the 50%, 25% either side of that, and then the 2.5 or 97.5% confidence intervals. So again, it's another way of characterizing not just the mean value, but the range of values within, or the range of outputs, and getting some handle on the variance associated with that. We might want to plot some of this. There's some really nice options for plotting these things out in SIMMR. So again, let's just run through these one by one. We can look at this a density plot here. So what we've got here, SIMMR output, and again, you can change these titles, you can save these. A lot more of those details are online. So what we're looking at here is that the relative contribution of littoral, profundal, and zooplankton to the population in a density plot. We can look at that similarly in a box plot if we prefer, and we can see here that we've got a pretty large contribution of zooplankton, smaller contributions of profundal and littoral. Similarly, you might want to look at that in for group 2, so the perch. And we've got much larger littoral contribution, smaller zooplankton, and a smaller profundal contribution. So essentially what we're seeing here is giving us a bit more detail than we had in the model and the stuff that we looked at previously, because we're incorporating the profundal in it. Yeah. The next thing we might want to do is one thing we want to do, and we talk about this in class quite a bit, is looking at these matrix plots. And here we're looking at, essentially what we're looking at here is the correlation. It's giving us some different bits of information. Okay, it's giving us the density plots in terms of a histogram, We're also looking at and these are quite important, the degree of correlation between different sources. So let's say here, and this is for group 2, we've got quite a high correlation, negative correlation between profundal and invertebrates and zooplankton. And that essentially is saying that if something has high amounts of profundal, it's likely to also have high amount of zooplankton. If something's got high profundal, it's got not much of an association, or high littoral, not much of an association with profundal, but a stronger association with zooplankton. And we'll talk in class a bit more about why that might be important. And essentially, it's kind of, we think about, everything is always going to sum to 1. Yeah, if we've got multiple different sources, you can only have 100% of contribution, total contribution. So if you're high in one, that means you're low in another. And it's important can be useful when you want to interpret the actual outputs of the model to know those correlations. Next thing we might want to do is to actually do some comparisons across either sources or across groups. So let's look here. We want to compare sources for group 1. I'm just going to run this line here. This will give us a couple of different pieces of information. First, it will give us a box plot with the comparison of the contributions for group 1, so a lot of zooplankton, some littoral, some profundal. And we can also get what's the probability that different sources are consumed to a greater degree than others. We've got a very high probability, almost 90%, that zooplankton is consumed more than littoral invertebrates, which are consumed more than profundal invertebrates. Much lower probability that we've got zooplankton consumed more than profundal, more than littoral, and almost no probability that profundal is the main dietary source for this population of consumer. We can do the same thing here for the for sources for group 2. And here, again, we've got very high littoral contribution. Remember, this is the perch that we were looking at, lower zooplankton, lower profundal, and our probability orderings here as well. Another thing we might want to do is actually compare between groups. So we've looked at the different sources that are going into a specific group, but maybe we want to say which of these 2 groups are using more zooplankton than the other. So we can do that here by plotting these out. So we see here group 1 is our whitefish, group 2 is the perch. We've got a box plot again showing the estimated distributions. So much higher contribution to whitefish than perch. Probabilities is pretty much 1 that we're almost certain, well, we are certain that zooplankton is making a greater proportion, is more important to group 1 than it is to group 2. Let's put it that way, yeah? We could do the same thing for other sources. Here, if we look at littoral, here, the probability that littoral is greater to group 1 than it is to group 2 is now 0. So remember, it's always the same order, but that means that group 2 is definitely using more littoral than group 1. Profundal might be interesting because I think there might be closer to an overlap. Definitely some more overlap, but more or a greater profundal contribution to group 1. And we see that at around about 0.9, 0.87. Okay, so a really nice, intuitive, easy way to interact with the data and pull out the specific things that we're interested in. I want to show you one last thing before we close out in this video, and this is combining sources. So we've talked a bit about this during the classes about how we may want to, or when we may want to, combine different sources. And we have a couple of choices that we can either combine these ahead of time, or we may want to come in afterwards and combine them afterwards, after running the model. And there's different schools of thought, but one of the nice things here is that this gives you an option to do this way, that you can run the model and then combine the sources and then pretty much run through the exact same comparisons. So let's say here, we want to run this to combine, say in this example, we want to combine our littoral and profundal into a single source called benthic. Yeah. So now we're no longer interested in whether, we're no longer asking whether these fish are feeding in littoral or pelagic. We're now saying, are they feeding, or rather, are they feeding in littoral or profundal? We're now just pooling those together and say, are they benthic or are they pelagic? So we can do that with this little line of script here. Make it run. And we can do our box plot here. So we're looking here for group 1, plotting with our combined sources. We create a new object now with combined sources. And again, we can see for group 1, greater contribution of zooplankton than benthic. And the same thing for group 2. Here we still have a much greater contribution of benthic than zooplankton, because now we've pooled together the littoral and the profundal in our perch here. Okay, I'm going to finish at that. That pretty much shows you how to make this work. Hopefully it's able to run for you. Hopefully you have no difficulty running it. The packages should all be updated and should all be ready to go. And again, Rich Inger and Andrew Parnell and Andrew Jackson on the previous version, give them, buy them a drink whenever you see them, because this work has made their work has made our work a heck of a lot easier. Rightio. I'm going to stop that there. And we'll see you all in the next one. So the next one of these videos, I'm going to look at Mixar, and that will allow us to actually stop sharing that. Yeah, so essentially the big difference when we go from SIMMR to Mixar is it allows us to run multiple models at the same time and sort of compare among these different models. So say we want to compare these different lakes at the same time. Yeah, we'll deal with that next. Okay, I hope you found this useful.